Good evening, everyone. My name is Amit Alon, and together with Yossi we did a project in Neurosteer. And Neurosteer has a portable wearable device that can measure your brain activity in real time. And you might not know this, but the way you sleep may have a major impact on your health. And you could get your sleep analyzed. You could go to a special lab. You would have to sleep there. You would have to wear this on your head along with other wearable hardware. And this is less than ideal. It's not ideal, it's expensive. So even if you get your sleep analyzed, you might just get it once. Neurosteer is offering a solution that might help take the technology of the sleep lab into the comfort of your own bed. Not only is Neurosteer's device portable and affordable, but if we look at the signal of an EEG, a full EEG, it's very noisy. It's comprised of a lot of channels. It's very hard to analyze. Neurosteer signal is much more approachable. Our goal in this project was to classify different sleep stages in hope of finding sleep patterns, complete sleep cycles, in Neurosteer's recordings. So basically, sleep is comprised of 4 different stages. We have the REM sleep, which is the longest of the 4 stages, and then we have the other stages that would sometime appear or not. Our goal was to detect these stages and try to find a periodic pattern within Neurosteer's signal and hopefully try to differentiate healthy sleep from sick sleep. So sleep analysis is something that has been done using full EEG patterns with prior knowledge of which channels are involved in which sleep stage. So what frequencies should we expect and stuff like that. Also, since there's a lot of data of EEG, there's a lot of label data. Here at Neurosteer, our goal was to do the segmentation in an unsupervised manner. So we don't have the labels that we need to do the classification, and we're trying to offer a segmentation. So what's the baseline of unsupervised segmentation? Clustering. So first off, we can take the signal and slightly denoise it by smoothing averages, and then just apply normal k-means clustering on it. So we know how many stages are in a sleep. We can add the waking stage, we can add disconnection stages, but we know how many clusters we're seeking. And we get some result, which would probably make sense, but the resolution isn't high enough. So we might be able to differentiate between sleep and wake. We might be able to detect the REM sleep, but we won't be able to detect all sleep stages, and definitely we won't be able to detect periodic patterns. We can also try to apply some DSP analysis, such as maybe entropy, to reduce the dimensions and try to find hidden frequencies. But again, this wasn't with high enough resolution, and we couldn't find any distinct frequencies. Not only that, when we look at different recordings, even from the same patient, even from the same sensors, we see that they are very different from another, which means that sometimes if I take something that might look like REM sleep in one recording and compare it to a REM sleep in another recording, they would be very different from each other in the original recording space. We could also try to look at the features themselves and try to see which features act like one another or which features hold a lot of periodic information and maybe try to derive some information from that. And yet again, the problem of inconsistency arises and the problem of lack of resolution arises. So we needed to find a new representation, something that would make the recordings a little bit more generalized, and this is why we moved to embeddings. So we moved to 2 different embedded spaces, which you can't really see. One was using diffusion maps. The other was using neural networks in the form of autoencoders. The first thing we're going to talk about is diffusion maps. What is a diffusion map? So a diffusion map is something that strives to describe the probability of moving from one point to another using one step of random walk. So if we take this 2D space and we have all these points, we will define what is called a kernel on it. And a kernel is a sub-environment of this 2D space which holds some of the points. And for this kernel, we will calculate the probability of moving from one point to another. And we have many such kernels. Each differs slightly in the points that they represent. The diffusion map will take all the kernels together and comprise one matrix defining all the probabilities of moving from one point to another. And the embedding of this would be the eigenvectors of this map. So this process could be very complicated. It could be very time-consuming, especially if we have a lot of time points. So to efficientate this problem, to make it more efficient, we comprise this pipeline, which is starting with feature selection of the original signal. Not all features of the original signal hold information regarding sleep stages. We can just disregard them. We then perform the embedding, apply manifold learning on the embedding to find the number of dimensions that we actually need, and then we can do embedded feature selection to get only the features that are really relevant for sleep stage segmentation. How can we do feature selection on the original data if I just told you that it's very hard? So if we take the original recording and we calculate for each feature its autocorrelation, we can use this decay time, the decay time from the autocorrelation, to divide these features into two groups, decaying features and features that hold periodic patterns. By only choosing the non-decaying features, we get a much more, a better representation of the features of the original signal that hold the information of the segmentation of the sleep stages, and this will be what would, this is what we'll eventually embed. So we took this high-dimensional space of the original recording, and we reduced it by embedding. Okay, now we have the embedding. How can we test if this embedding actually represents something relevant to sleep stages? So it turned out that we had some label data, some manually labeled data, just a handful of recordings. And we took a specific recording from a specific patient, a specific night. We trained a simple classifier on it. We started by simply classifying sleep, non-sleep, and REM, non-REM. And when we look at the model, and in blue you can see the F1 score of the embedding, and in red you can see the F1 score of the original features, you can see that the embedding really outperforms the original features. And we built many such models, 50 features, 20 features, 8 features, and even only 3 embedded features. And in all of them, for a simple classification task, the embedding completely outperforms the original features. By the way, you see this distinction here? It's an interesting distinction. If you're interested, come ask me later. What happens when we try to classify all sleep stages at once? Well, this is where this model falls short. So embedding in this case isn't good enough. It can't classify all stages at once, but we showed that this embedding is very good in the simple task of classification of sleep, non-sleep, REM, non-REM. Why is it failing on multi-class classification? Many possible reasons. The 2 main reasons are, first, the model I presented shows what happens when I take one step in a random walk. But what would happen if I expanded it to take a random stroll? Then it might get the segmentation better and could classify more labels at once. And also we found that some of the label data was pretty noisy, so probably the labels aren't that good. Now Yossi is going to talk about the second method of embedding.
Thank you. So I will use a paper. I don't remember anything. Sometimes I even forget my name. So we all know that neural networks perform surprisingly well on several machine learning problems. But what makes them so great? I think that finding a good representation of the data is what makes them so good. In general, a good representation of the data is one of the keys to the right solution in any computer science problem. In supervised learning, the representation of the data is built from the labels and the loss function. But what about when we do not have labels? In unsupervised learning, the loss function plays a more critical role in designing the representation of the data. So what can we do in unsupervised learning to create a good representation? We can add one solution is to add prior knowledge from the problem domain to the loss function. We will see it in a minute. So to get better representation of the data, we chose to use the autoencoder. Autoencoder is an elegant and classical neural network that is designed with two major principles. The first one is the output of the neural network should be the same as the input. The second one is there is a bottleneck layer. You can see it in the diagram. This bottleneck is where we get our new representation, and the dimension of the bottleneck layer should be lower than the output layer. So autoencoder is an excellent dimension reduction tool. You can easily create any linear, nonlinear reduction function with an autoencoder. The simplest example is PCA. You can easily create PCA with just one hidden layer and linear activation function. If you want to prove that how powerful autoencoder is, you can see the recent publication from DeepMind. They just present a new human picture that are generated from variation autoencoder that looks better than the state-of-the-art gun. So how can we add prior knowledge to our model? We know that sleep stages are steady. The sleep states are steady, but the EEG vectors are very noisy. So we try to remove this noise from our new representation. In order to do so, we use triple margin loss to make sure the temporary closed EEG vector will transform to similar embedding vectors. We also want to remove the device noise. So we add a syntactic noise to the data and make sure the embedding does not change with or without our noise. We also know that there are several simultaneous processes in the brain, but we want to separate them. So we add a loss that eliminates the correlation between our embedding channel. The next loss was just to make sure all the embedding vectors are in the same norm, so it will be easy to compare between them. And of course, the last loss is the reconstruction loss between the input and the output. So it was pretty hard to evaluate our model because, like Amit said, we have limited amount of labels data, and the labels are not always coherent. Nevertheless, we tried. So we trained two logistic regression models from a single record. Record is one night sleep of one patient. The first model was trained on EEG data. This was the baseline, and the second one was trained on our embedding data. We test all the models on all labels record that we had. The test models. So the result. First, we try to classify all sleeping stages, but this won't work so well. We try to improve the baseline, but with no significant. So we try to understand what happened, and we check the labels and saw that they are very noisy. This means that they are not reliable. But we also saw that the REM sleep, the most important stage of sleep, are more stable than the other stages. So we try to build a binary classifier just for REM and not REM. And this worked better, and the improvement is much more significant. My hope from this method was to manage to separate processes in the brain, so it will be trivial to detect sleep stage by only one channel. We managed to do so. You can see in the graph, but it wasn't a stable process, and it's not consistently across all our record. So I believe that with a little bit more work, it will be possible. Thank you.
So what's the impact on Neurosteer? So first of all, we offer two methods for embedding that we show are generalized. We show that the embedding holds information regarding sleep state segmentation. So our hopes is with a little bit further analysis, a little bit more work, Neurosteer could take these models, they could apply clustering on the embedding that we suggest, and later on they can train a classifier to actually detect the sleep stages and hopefully turn this into an online classifier of sleep stage detection. Thank you very much. We would like to specifically thank Tomer Lotterman for Neurosteer for the great mentoring, and Mykola Maksimenko, our Yandex assigned mentor. And thank you for listening, and have a great night's sleep.